everybody. Let's think through all of the details of modeling the path a point on the perimeter of a rolling ball will make. So if I have a ball that's radius 2.5 and I want it to roll without slipping so that it completes one full rotation by time equals 7, we have to think about a couple of things. We have to think about how fast horizontally does it need to slide, and then how fast does it need to rotate so that it's as if it's rolling without slipping. So we could imagine the ball this way. Here's the ball at time 0 with an upward facing vector. Sometime later, at time 7, so this is t equals 0, at t equals 7, we want it to have gone through one complete rotation so that we're facing back vertical again. Okay, so let's figure out the parts separately. Let's figure out the rotational rate. So remember, rotational rate is just how far did the angle change in a certain amount of time. So one full rotation would mean 2 pi radians, because that's one full circle. And it needs to happen between 0 seconds and 7 seconds. So that would be every 7 seconds. So this now gives me the rate at which I need to rotate. So let's add that in here. And you can just double check that this makes sense. If I plug in time 0, this inside of the sine function becomes 0. And so that means I'll be finding the sine of the angle 0. 7 seconds later, I'll plug in 7 here. 7 divides 7, and my angle will be 2 pi. So I went from an angle of 0 to an angle of 2 pi. If you remember from last video, though, I don't want the angle at time 0 to be angle 0. That would mean it would be facing this way. I actually want it to start facing up. So we'll add a pi over 2 at the beginning. And then I also want to be sure that the ball is rotating clockwise. And so I'll end up subtracting the time, because that means as time increases, the angle is going to get smaller and smaller, so it'll be rotating in the opposite direction. Okay, so I think we've fixed everything related to the rotational rate. If that's all we did, though, there's no guaranteeing that the ball will have translated exactly one circumference worth. Because remember, if it completes one rotation, not only does the angle go through 2 pi radians, but we've rolled around the entire perimeter of the circle once. So if it's a really big circle, it's going to go a long way because it's got a big perimeter. If it's a tiny circle, it'll just go a tiny way because it's got a small perimeter. So the next question we have to ask ourselves is, how far does it actually go when it completes one full rotation? Well, we decided that the perimeter is the same as the circumference of the circle. So here, that'll be 2 pi times the radius, which is 2.5. So that gives us 5 pi as the circumference. How long did it take us to travel 5 pi feet, let's say? It was 7 seconds. So my speed is going to be 5 pi feet every 7 seconds. So this gives me my horizontal speed. And I can put that right here, because now that's saying, so imagine it this way, if time is 0, that vector is length 0. If time is 7, 7 divides 7, and my vector is length 5 pi. So in 7 seconds, it stretches to be exactly the length I need it to be. That's all there is to it. So all you really need to do is think clearly about what does each vector actually control, and then ask yourself, if it's going to make one full rotation, what does that mean for rotational rate? How many seconds does it take to rotate 2 pi radians? And then for the translation to work, you have to ask, if I'm going to rotate one full perimeter, that means I have to travel the same distance as the circumference in a certain amount of time. And so you can calculate what that is, and that gives you your horizontal translation. Let's look at this question, which is very closely related. So here it says, what if I want it to be moving horizontally at 5 feet per second? Think for a second about what exactly is moving at 5 feet per second. Some groups thought it must be this point at the top of the ball. But I hope if you can imagine the ball kind of moving at a constant speed, the point at the top of the ball is going to be going faster and faster as it approaches the top here. So it's going to be going quite fast as it turns over the top. And then as it approaches the ground, it's actually going to pause for just a minute as it touches the ground here. So its speed will become 0 and then increase until it's going fast and then go back down to 0 again. In other words, the point on the perimeter of the ball is actually changing speed all the time, and it would be rather difficult to figure out how to make that travel at a constant speed. So what I must mean is the more intuitive idea that the center of the ball is traveling at a constant speed of 5 feet per second. All right, so let's draw our picture again. If it's traveling at 5 feet per second, that means after 1 second, it will have gone 5 feet this direction. But I don't know how much of a full rotation that is. But I feel like that's the thing that's going to really help me come up with my rotational rate. Because remember, if I know change in angle over change in time, that's how I get the rotational rate. And I know a change in angle is easy to find if I've completed one full rotation. So let's try and ask the same question. If I'm traveling horizontally at 5 feet per second, how long does it take me to make one full rotation? Let's write down what we know so far. The first vector that takes us up to where the center of the ball starts is just the same. The second vector controls our horizontal motion. And here it said I'm traveling horizontally at 5 feet per second. So I can just make this 5. Again, you can always double check that it makes sense by plugging in time 0 and see that we're at horizontal location 0. If I plug in time 1, that means I've traveled a horizontal distance of 5. So in other words, 5 feet after 1 second. So that works. Let's look at the third part. Okay, I've sort of turned it around the corner here. All right, so we know the horizontal speed, but remember we have to match it up with the rotational rate. So how long, if we know a change in angle and a change in time, that gives us the rotational rate. So I want to use 2 pi, 1 full rotation, as my change in angle, but how long does it take to do that? Well, in order to figure that out, I have to ask, at what time does it end up over here? Well, where is it over here? Oh, it must be 1 full circumference worth. Remember, the circumference was 5 pi, which I got by figuring out 2 pi times the radius. So now I can ask myself, how long does it take me to get to 5 pi? Well, I know that I am traveling at this speed, 5 feet per second. So the question is, what's the time where if I multiply the time by 5, I end up at 5 pi? I mean, you don't even really need to do algebra here. The time must be pi. So pause for a second. The key moment might have happened a little bit fast. But all of these problems are very simple if you can just ask yourself the right question for what is it that you really need. I needed to figure out rotational rate. I know that the rotational rate is change in angle over change in time. I think, okay, a full rotation would tell me my change in angle. How long does it take? So now I have a new question. How long does it take to make 1 full turn? Well, I know how fast I'm going horizontally. So I know that after 1 second, I've gone 5 feet. After another second, I've gone 10 feet, and so on. So I can set up an equation. I can say there's some mystery amount of time where if I multiply it by 5, it will take me to the distance I want to be at. And that's where that equation came from. Okay, so now that I know that the time it takes is pi seconds, I can find my rotational rate. Because I know the change in angle is 2 pi. I know the change in time is just pi. So that gives me a rotational rate of 2. Remember though, I still want to start at an angle of pi over 2, and I still want to rotate clockwise. So I'm still subtracting the time. But the speed, the rotational speed, is going to be 2. So pi over 2 minus 2t. Let's take a look at an animation of that one. So here's the equations. First, let's check that I'm traveling at the right horizontal speed. So at time 0, I'm here. If I go over to time equals 1, you can see that the center of the ball lines up with 5. So that means in 1 second, I really did go horizontally by 5 feet. Okay, now let's watch the full animation. So it does look as if I'm rotating without slipping at all. And you can see that because when I zoom in here, there aren't any weird loops or anything. The single point on the perimeter hits the ground and then goes back up again. Let's do the last problem. The last problem says, what if we keep everything else the same, except now I want the ball to start at x equals 15 and roll to the left at the same speed? Let's start with the equation that worked for the last problem. Okay, here we are. So now we want time equals 0 to start here, and we want the ball to roll that direction at the same horizontal speed. So if I were you, I might pause the video and think about which parts of these need to change and how do they need to change. Because I think if you really understand all the pieces here, it's just a couple changes that are very easy to think about. Okay, so this vector is not being affected by time, so it should point us to our starting location. Before, the starting location of the center of the circle was just up by 2.5. Now it's going to be over by 15 and up by 2.5. So in the new equation, let's go over by 15 and up by 2.5. Okay, let's think about how this one needs to change. Here, this vector was stretching right as time increased. The new one, I want to stretch left as time increases, but I want it to change by the same rate. So here, I can just have it point in the negative 5, 0 direction. All right, what about the rotation? The 2.5 is still the same because the radius of the circle is still the same. Only now, a couple things are changing. As time increases, I want to be rolling this direction, so that means the rotation needs to be counterclockwise. So it's like we had at the very beginning of the last video. Instead of subtracting my time to get an angle, I'm going to go back to adding it. Do we still want to be facing at an angle of pi over 2 at time 0? The answer is yes. So we'll keep that part just the way it is. Has that fixed everything? Yep, that's it. So here, let me rewrite it, and then we'll take a look at an animation and convince ourselves that it works. Okay, so I've removed the circle from the Desmo sketch because the circle didn't follow the right programming. However, the circle was not the main thing. The main thing is the path and the tip of the vector that traces out the path. And so you can see here at time 0, we really are at 15. And then as time increases, the tip of that purple vector really does simulate a ball rolling in the opposite direction.